So one thing we do know is the global mean temperature increase. This is basically the observational evidence of global warming. Now, normally the way this is presented is that the globe is warming, and then we try and work out why. Actually, it's the other way around with this. It would be amazing if the globe was not warming at the moment, because all of the physics we understand about the system suggests it has to be warming. Okay, but it has warmed by 0.8 degrees, and this is the global warming record. I can show you other global warming records. They would all agree very strongly on what's been going on here. And what we've got is a non-continuous increase in temperatures here, but most of the warm years being in the recent past, in the last 30 years. Now, there's a debate about whether it's flattened off here. It appears to have flattened off, but we believe that's just to do with ocean heat uptake anomalies, most likely. The amount of energy that you get for a certain amount of greenhouse gas depends on how much energy gets dumped in the ocean, and that varies from one period to the next. The other thing you notice about this is it's not a smooth increase. There was a period of cooling in the mid-century, which was bizarrely due to another of our pollutants, sulfur dioxide. So for a while, two of our pollutants were cancelling each other out. Sulfur dioxide is really bad for you, so we've been cleaning it up. But as a result, we've got a bit more global warming. Okay. And the evidence of climate change in the things that we expect to affect most, like the cryosphere, the snow and ice, is very strong indeed. So there was a new record low recorded sea ice extent in the northern hemisphere. This is what we used to get, 2.72 million square miles at the minimum. It was about half of that in 2012. So the cryosphere is responding extremely strongly to something, and it seems to be global warming. And the reason that's happened is because CO2 has gone up. We can measure that as well. We can measure the signature, the isotopic composition, liquid isotopic composition. We know it's fossil fuel, and we also know how much CO2 has been put out by humans, so it's completely consistent. This is the very famous Keeling curve, produced by this guy, Dave Keeling, at the Mauna Loa Observatory on Hawaii. These oscillations here are to do with the northern hemisphere vegetation sucking down carbon dioxide during the summertime and releasing it during the winter. So this is basically a result of the fact there's slightly more land in the northern hemisphere than the southern hemisphere. And this very long record shows the continuous increase in carbon dioxide that's driven by fossil fuel emissions. And in the context of the longer term, so this is going back to the last ice age, and almost every ice age that we can see, carbon dioxide was about 190 parts per million. It then went up in the interglacial periods, which are much shorter duration, to about 100 times higher than that, 100 ppm higher than that, about a third higher, which is 280 to 270. And this is our recent increase on the same scale. And so the thing to notice about this, it is like a glacial change in CO2, but about 100 times faster. And it's the rate of change that worries us. If you push the system really fast, the normal stabilizing things can't operate. Okay, I'm not sure, this might not play actually, will this play? Let's try. Okay, so this is something, I'm not sure how well you can see this. This is something I downloaded from the internet, thanks. And what you see here, first one, is first of all that where I came from started a problem. The industrialisation here, first of all, so we know about the fossil fuel problem. And you can see it spread out here, so this is the global emissions of CO2, and you see them going up and driving that CO2 increase through time. You see the sort of world waking up to fossil fuels here. First of all, in North America, you'll see Asia. By the end of this, you can see it's very much a shared problem. Not by the whole world, incidentally. The developing world is not causing the problem, but will be recipient of lots of negative impacts. So it's kind of pretty, actually. And if we were just worrying about development, we'd say that's a good thing. But of course, what we've found is that what's fueling this development is detrimental to the system. So somehow we've got to have development that doesn't lead to CO2 emissions like this. So the main point about this is we know very well, and very few people argue about this, where the CO2's come from. We know we've emitted more than enough CO2 for the CO2 rise that we see in the atmosphere. And the reason it hasn't risen faster is because the natural sinks in the land and ocean have kept it a bit lower, have absorbed about half of our emissions. The other thing we know is that CO2 is a greenhouse gas. This is not something that we made up. CO2 has molecular properties. Let me show you. So this guy, Svante Arrhenius, very brilliant physicist, actually warned of global warming due to CO2 emissions in the late 19th century. So he estimated that the sensitivity of the climate system to doubling carbon dioxide will be about 5 to 7 degrees. And all the climate scientists travelling all over the world, burning jet fuel, got this to 1.5 to 4.5. So Arrhenius was pretty close. The thing about this is that it means that we had a theoretical basis to expect warming due to CO2 long before we could see it. And that's why there's a lot of relatively confident statements from climate science about this. It's totally consistent with what we would have expected. It's not like we saw the global warming and thought, oh goodness, what could that be? And came up with something. This is exactly what you'd expect. And here's this paper which I love. This is philosophical transactions of the Royal Society in the UK. I've underlined just from 1896. Is the mean temperature of the ground in any way influenced by the presence of heat-absorbing gases in the atmosphere? And the answer to this was yes. So Arrhenius at least knew this was going to happen. We might have not listened. And this is why. So this is a very high resolution microscope picture of carbon dioxide molecule. So you can do it with PowerPoint these days. So there's carbon atoms, two oxygen atoms. And when the Earth warms up, because of absorbing solar radiation, it emits largely infrared radiation, and some of that radiation resonates with the CO2 molecule such that it bends like this. So look, sometimes called this a Mickey Mouse nose. It's like ears and nose going like this. And actually the quantum mechanics behind this is very well known. So what that does is it means that greenhouse gases prevent the system from behaving like a black body. This is what the energy you'd see being emitted by the Earth would look like if there were no greenhouse gases. And what you actually see are these huge chunks taken out of it by greenhouse gas absorption. That's actually a good thing because it's kept the planet warmer than it would be, but we're making these chunks bigger and bigger. So the one that we've just seen, that oscillation there is 15 microns. There's this gap here. So we know very well why we see these gaps. Very well known science. Okay, and there's now a huge body of evidence that climate change is human caused, not just because we've got a theoretical basis for it, but because we can now do analyses of the trends we see and compare the statistics of what we see in the observations with what we would see in a model with and without different effects. And this is one of the main things that's come about out of the Intergovernmental Panel on Climate Change, which I'm a very small part of. So this was set up in 1988, produced its first report in 1990, and has really driven the United Nations Framework Convention process ever since. It has 3 working groups here. So overall, there's a lot of scientists involved in this. Thousands of scientists, in fact. And the governments participate in this as well. So it's an unusual thing in the sense that, first of all, to get scientists to agree on anything, as you'll find out later, it's difficult. So when they do agree, you probably should listen. Probably, maybe not. And then to get governments to endorse, in some sense, what scientists say is also quite unusual. And there's always a tug of war here, with some governments preferring some things not to be said, and some scientists saying, this is the truth, we must say it. And so there is a process by which the IPCC reports are made very robust. I think it means they're rather cautious, actually. So the things you see in the IPCC report are, each individual scientist may say slightly more extreme things, but it's very, very robust. So the IPCC has already produced 5 reports in 1990, 95, 2001, 2007. Next one's just about to come out. It won the Nobel Peace Prize in 2007. So I can claim 1/3000th of the Nobel Peace Prize. Quite pleased with it. I've never been that peaceful. And the next report's due out actually in September of this year. And this is just the stats for this one. So they get bigger and bigger every time. I don't know how much carbon is locked up in IPCC reports, but it's one way to produce a carbon sink. As long as no one ever burns them, we'll be fine. There are 830 scientists and review authors involved in this in many countries. So it's a huge process. And in fact, it's got to the point where it's almost unstoppable. I mean, if policymakers said we're no longer interested, I think the juggernaut could not be stopped. Climate science has a huge inertia now. Okay, what it has done is many interesting things, including bringing people together to discuss what we do and don't know. One of the key things is this, that the human fingerprint of climate change is detectable. That is to say that we can put very precise probabilities on the likelihood that the warming we see is not human caused, and it's small. It's like 5%. So it's 95% chance it's human caused. And the way this is done is, I've gone too far, is that you take the global warming record that I showed you. This is this red one here, slightly different form, so we've got this mid-century cooling and the recent warming. And then you take a climate model that contains the physics of the greenhouse effect, the impact of particulates on the system, variations in the sun, variations in volcanoes. And then in this case, we just look at the natural factors, volcanoes and the sun, and we find that the green, which is the kind of range of model responses, is able to reproduce reasonably well the record up to about 1950, 1960, but it just cannot reproduce this, whatever we do with it. We can't make the sun's output just does not vary enough to reproduce this. Whatever you might hear, it's nowhere near enough. But when we put the greenhouse gases in, and the radiative balance of this is, as I showed you, we know quite well, we do a decent job. So we can work out from this what the likelihood is that the climate system just had a wobble and produced this warming without it being anything to do with us, and it's extremely low. So you hear this, these statements like from the IPCC that are actually couched in language that really mean numbers in terms of probability. It's basically a 95% probability that it's human caused. The other thing, and this is less clear, you can't clearly link this to climate change yet, weather and climate disasters seem to be becoming more damaging, and this is where you generally go to the insurance industry who really care about these things. This is from Munich Re. There's the overall cost in billions of US dollars of climate and weather-related disasters, so including things like Katrina here. It doesn't go beyond 2007, this one. And this has been, this is not about economic growth, this has been normalised to 1990 values. So there is a huge increase in damage, as you could say. This is because we build in more and more vulnerable places, there are more and more people, could be so. But you can also see there's a tendency for extreme events and extreme damages to increase. And we would expect that to some extent. Okay, so if you're just worried about the business case, you'd say climate change is a real issue. And there is some science that suggests, at least in the Atlantic, that the power of hurricanes, which is shown by this dotted line here, has had a very significant increase in terms of the damage they cause. This is from a guy called Emmanuel, who was at MIT. And this is correlated with the way the oceans form. That's the continuous line here, very well correlated. And this is partly because hurricanes are driven by ocean surface temperature, so you would expect to see this, but this is an extraordinary correlation. So there is circumstantial evidence and some physics to suggest that some extreme events will increase under climate change. I'm nearly done now. Right, so what do we do? So the United Nations Framework Convention on Climate Change aims to stabilise greenhouse gas concentrations in the atmosphere at a level that will prevent dangerous anthropogenic interference with the climate system. So this is this notion that you stabilise the system and so that nothing really terrible happens. And recently, the UNFCCC of the Copenhagen negotiations defined dangers of 2 degrees of global warming. So this is the value you hear as the thing we've got to avoid, 2 degrees. Okay, now, we can argue about what dangerous means, but this was the motivational target that was chosen. And actually what that requires is the global CO2 emissions that are shown here from 1850 onwards, going up very steeply. These units here are billions of tons of carbon per year in the form of CO2. In order to stabilise that, and we did this calculation in the year 2000, you have to have emissions stabilise and come down the other side. And in 2000 we thought, oh, we've probably got a bit of a while, we've probably got to 2015 or 2020. And there we are in 2030, so it's getting a bit closer. The thing about this is that you, in order to stabilise with conventional mitigation, which means reducing CO2 emissions, you have to cut global emissions by 60% by 2050. And then you have to have them come continuously down here. And the reason why that's the case is because around about 20% of our CO2 emissions stay in the atmosphere for extremely long, almost forever, 100,000 years at least. So 20% of what we do is irreversible, essentially. So it's a tough ask. Actually, what's been going on is that CO2 emissions have gone up very significantly since the Kyoto Protocol came into force around 2005, I think, and it was penned in 97. There isn't much sign from that there's any break. The only point there was a break was during the recession of 2009, and then there was a recovery. So it's a good thing that the economy recovered. It's a shame that the CO2 emissions did at the same time. So there's no sign of this turning over. I can't imagine it just going off the page and doing that. I mean, It'd be nice, but I can't imagine it. So we've got a major issue. If we want to avoid 2 degrees through conventional mitigation, we're getting very close to I think we're past the point where we can do that through conventional mitigation. Okay, so that means we either have to accept a lot more than 2 degrees and adapt to it, or we have to find other ways to control the climate system. Right, so what else could we do? So these are the things that we will all be arguing for in different ways after the break. This is a way that some people deal with this problem that looks difficult, is to suggest it doesn't exist. I also do this with the washing up at home. It doesn't go away. So this is basically putting your head in the sand. Not very comfortable after a while. But this is, believe it or not, this has got a lot of people who would like to happen. Difficult problem, as the thing does happen. You can focus on adapting to inevitable climate change. We've got some climate change already. We've got some more frozen into the system because of inertia in the system. We're going to have to adapt anyway. This does require that everyone has the resources they need to adapt. So adaptation requires some redistribution of wealth, which is not something that humans are very good at either. Or you pour some other levers on the climate system, and some of this is getting quite radical. I spoke about this last night. So if we look at the overall impact of the different pollutants and the different changes that humans have done to the system on the climate system, we can measure this in so-called radiative forcing, which is the amount of extra energy in watts per metre squared that we've put in the system because of these actions. Okay, so we put CO2 in, it's a greenhouse gas, it means it's a net warming of the system. We can calculate that as an energy per unit area. And remember, these numbers are quite small, really. It's only 1.6 watts per metre squared that would produce a very significant climate change. So think of a 100-watt light bulb on a 10-metre square. That's the equivalent energy imbalance we produce in the global climate system. So CO2 is the one that we always worry about, and that's what nearly all the negotiations we're talking about. But it's almost a fluke that the overall forcing, which is shown down here at the bottom, which I'm standing in front of here, is about the same, very close to being the same as the CO2 forcing right now. And it's a fluke because the other warming factors that are things like methane, nitrous oxide, tropospheric ozone, and are being cancelled at the moment by the effects of the particulate pollution we put up. So that thing that produced the mid-century cooling, which is sulfur dioxide mainly, made clouds brighter, reflected some sunlight. And so you can convince yourself that these things are balanced, and they'll always be balanced, but they're not going to be, not if we're sensible, because these factors here are associated with sulfur dioxide, which is really horrible. We don't really want it. So as we clean up the air, these get turned down, and you get an additional warming revealed from the other components. So some people are now arguing we should concentrate on these, because they're faster to react, associated with improvements in crops, and also with better human health. And others are even suggesting we should try and tweak these back up, not by making the troposphere dirty again, but by putting particulates up in the stratosphere. It's called geoengineering, and that's seriously being discussed, at least by some scientists, even if it's not yet being discussed by policymakers. The idea here is that if you can't reduce the thickness of the greenhouse blanket by taking CO2 out or mitigation, you could just make the blanket brighter, so that in the daytime it doesn't absorb so much energy. And you could do that by putting bright particles at the surface, up in the air, even something in space. This turns out to be ridiculously expensive. Or, most likely, by putting aerosols in the stratosphere like a volcano does to cool down the system. So this is really radical monkeying with the system. And I hope at least it convinces you that, that scientists at least think this is a serious problem. That if we can't solve it through the obvious way, then we might think about some crazy stuff. It's a kind of threat. So humanly produced climate change is definitely happening. I think we carry on arguing about this sort of, and it's ridiculous because we've just got to get on with dealing with it. There is increasing evidence of weather extremes becoming more frequent. This is a much harder thing to say with any degree of confidence, and it's almost circumstantial. So the next IPCC report will not be definitive about this, I don't think. But it's clear that the damages associated with weather are going up. the work of thousands of scientists suggests that unmitigated climate change would be difficult to adapt to. So we've got to do something else as well. So there's a whole load of things we can do, and I listed them before. But we've basically got to start thinking a bit more laterally, I think. And I'm going to leave it there. Thank you for your attention.